So again, as I mentioned, welcome to Combustion 100, a free webinar by TruTechTools. We're going to take about an hour to give you an overview of combustion science and the application of combustion analyzers. You'll notice here on the screen we have on the left, it's a brand new analyzer by Testo. There's two new ones actually, the 310 and the 320, some pretty new exciting equipment. And also Bacharach has some new analyzers, the FireRate Insight Plus and the FireRate Intech. We don't get too much into analyzers until near the end because we're talking mainly about the science at this point. But if you have any questions, feel free to give us a call on our toll-free number to ask about the products. So if you aren't familiar, TruTechTools is one of the largest internet distributors of test and measurement products. We put together a team of professionals that know how to deliver the CEU training that energy auditors, HVAC, and related trades would need to help perform their jobs better. We have a total of 45 years combined experience, and we try to deliver hands-on related training that will be practical for the work you're doing. This class does qualify for up to one BPI CEU. If you're listening to the live class, unfortunately the recorded one does not qualify. So if you're hearing the recording, there's no CEUs available. If you have any questions about that, we have a couple slides going through where you can submit your information if you haven't submitted your credentials already. So if you do require BPI CEUs, please remember full attention is required. They actually have a tracking system that's built into our webinar program that will keep track of how attentive you are. If you surf off to other screens, that will ding you on attentiveness. It's good to ask a question because that's also recorded in the system. And basically BPI reviews how attentive you are, and then we'll award up to one CEU. But if you're less than fully attentive, you may not even get a full CEU. So that's the situation. The situation's really in your control and out of our control. It's about how you pay attention, interact with, and listen to this webinar. If your BPI number that should have been entered at the time of registration, if not, you can email that to Marilyn with marilyn@TruTechTools.com with your name and the date of the webinar and then your BPI certificate number, and we'll be able to submit that properly to BPI. The submission process takes us a couple days to get it in, and it takes BPI a few days to register in your account, so please be patient. If it's been more than 10 days or 2 weeks, you can let us know, and we'll get involved and see where your CEU credits are at that point. So the real basic agenda today, we're going to try to convey and help you increase your understanding of combustion and combustion efficiency. We're going to look at some of the common causes of CO and CO safety issues, and also how to perform a complete combustion analysis with a digital combustion analyzer. And we'll also get a little bit into heat exchanger examination and testing, because heat exchangers with warm air furnaces and warm air heaters, some of the flue products getting into the distribution air size can cause some real issues for health and safety. So we do want to cover that important point. So why would you even want to perform a safety or an appliance test or a performance test on a product? Well, of course you want to perform a safety test because it would ensure the appliance is operating safely. It also helps both the owner and the contractor minimize reliability by getting in there and taking a measurement. Doing a tune-up or checking how the equipment is running can assist you in preventative maintenance and activities, which will help with fuel savings. And this is especially true for commercial accounts where there's higher BTUs, higher fuel consumption rates. But even in residential, having a preventative maintenance check with a combustion analyzer can tell you loads of information about how the equipment's running. This can also help improve a technician's, a contractor's professional image and their company's image, and also help to demonstrate to the equipment manufacturer that they work with that they're actually going out there being proactive and making sure equipment's installed correctly to the manufacturer's stated and required guidelines. All these things come together to really help out the whole process of installing, maintaining, and servicing equipment. A contracting company and even an audit company can perform quicker service calls, quicker audits by having a digital combustion analyzer, and then for a service company, minimize those callbacks that can come up because you're actually taking measurements and you have more information at hand to make a more decisive action when it comes to combustion equipment installation and maintenance and running. We're also doing this to ensure the customers that you're interested in the customer's safety and security. And there are national installation verification programs that are running and starting up and running in various areas of the country. And right around the corner, really here in a lot of states, is the ACCA, or the Air Conditioning Contractors America Quality Installation Program. Now, while it doesn't require the use of digital combustion analyzers, they are recommended as a tool, and it's really a good way to get on track with performing a quality installation. And shortly after that, we'll be talking about, or the country will be talking about, quality service and maintenance. So these things are all playing together here. Another thought, another question we often get is, why would I want to test an appliance that's unadjustable? Many times people consider that, especially residential warm air heating systems, furnaces, that they are really plug and play, and that couldn't be further from the truth. In addition to having to be installed correctly with the right kind of airflow, the right fuel pressure, real basic issues, you also have to recognize that the equipment's installed in a dynamic environment. There can be changes in the combustion air zone, and this can be true especially when you have atmospheric fired combustion. Not so much of an issue with sealed combustion, but atmospheric pressure changes can change the way the combustion system operates. Fuel pressure can change the way the system operates. I've seen firsthand fuel pressure changes and fuel quality changes at the AGA labs, which can lead to changes and variations in the way the combustion equipment operates. There can be changes in settings of blower speeds for various reasons. Either technicians or owners can change the blower speed, which would change the way the heat is extracted off the heat exchanger, which can change the way the appliance operates. Duct sealing, again, can affect the available air that's flowing into the combustion air zone. Anything in the environment itself, including cleaners or paints or paint thinners, that kind of thing, can get into the airstream in an atmospheric system and then start to corrode or rot or interfere with the way the system performs. And then even the installation itself, if it's not done correctly, again, with the correct airflow over the heat exchanger and the correct fuel pressure, can compromise the way the equipment is intended to operate. And all this really is, we're doing it for the safety and the performance for yourself and for the consumer. So basic combustion theory, let's get into it. Real simple definition here. Combustion is a chemical reaction. So we will be talking a little bit about chemistry. Not at a very advanced level, but we will be talking a little about chemicals, because that's basically what combustion is, a chemical process. It's actually a rapid oxidation, which is the mixing of fuel, oxygen, and a source of ignition to release additional or excess heat, release the heat that's trapped inside the fuel itself. So in order to make this happen, we have to have three things come together, and sometimes they're called the combustion triangle: fuel, oxygen, and a source of ignition. And they have to be in the correct ratios, but usually this is what the manufacturer is providing in the appliance, is fuel, oxygen, and a source of ignition. Those are the three main things required. So if we take a look at this picture and this diagram, we have, I'll pull my laser pointer out, we have oxygen, we talked about, fuel, and heat. And that would be the source of ignition, heat here. The fuel is a H and C we show, which is a hydrocarbon-based fuel. It's a combination of hydrogen and carbon molecules, atoms, to produce various molecules. And the most typical one is natural gas, which is CH4, or propane, which is C3H8. Those are the kind of fuels you can have. So on this side, we have oxygen, fuel, and a source of ignition or heat. When complete combustion happens, we get more heat that's released from the bonds in the fuel. We get carbon dioxide produced, CO2, and it's very different from CO. So let's make sure we understand this. CO2, carbon dioxide, which is very different from CO. We'll cover CO in a little bit. And water, H2O. You can easily see here you have the oxygen, the O's, coming through in CO2 and into the H2O, water. And we have the H's and the fuel coming through in the water vapor, and the C's, the carbon in the fuel, coming through in the carbon dioxide. So everything is chemically balanced here. And we've also released this additional amount, this larger amount of heat than the heat we put in is the heat that's been transformed and comes out. A combustion analyzer looks at everything on the bottom side of the equation. You can measure and control sometimes the oxygen going in, the fuel, and the source of ignition, but the output in terms of how complete the combustion is can be measured by examining these three things on the opposite side here: the heat, the CO2, and the water vapor. And we also call this undiluted combustion. And undiluted comes from the fact that we are talking about oxygen, pure oxygen, coming into the combustion system. That's not always the case. In fact, most combustion systems use air. And let's take a look at what air is. Air is a combination of nitrogen, primarily nitrogen and oxygen, about 78% nitrogen and about 21% oxygen. So the oxygen we're using to burn comes through with a whole lot of nitrogen coming along for the ride. So in order to get 2 cubic feet of oxygen, which may be required in a combustion process, we have to bring along 10 cubic feet of air, because only 2 of those 10, or about 1/5, is actually oxygen. And the oxygen is what is really used by the combustion system. So air is basically 1/5 oxygen, the rest of it's nitrogen, and the nitrogen comes along for the ride. And so we'll be talking about the impact of that coming along for the ride shortly. So here we talk about the problem with using air, if you want to call it a problem. It's very convenient. It's around us, but because the air we use is the oxidizer, and it contains only partially oxygen and the rest nitrogen, perfect combustion can never be achieved. There's always that additional nitrogen there interfering with things. Also, large amounts of heat energy are absorbed by the nitrogen in the air as it moves through the combustion system, and that plays no role in the combustion process. That just moves up the stack. So in a way, we have a little bit of compromise because we're using air and not pure oxygen, but air is very convenient to have. This by no means, there's very safe and easy ways of operating with this, and the manufacturers have figured out the perfect way to use air as an oxidizer in combustion systems. Now we move to incomplete combustion, and this is where we're going to introduce the fact that we're using air and fuel and heat. So we still have 3 things on this side, but instead of just oxygen, we now have air with the nitrogen in it, and it's a larger mass. It's a little bit bigger than the little blob we had before we were looking at. Also, whatever is contained in the air can also move through the combustion system. So in incomplete combustion, we don't go all the way to forming just CO2 and water vapor. We end up stopping partway in the combustion process and forming carbon monoxide. That means there wasn't enough oxygen around where the fuel was being broken down and combusted and oxidized to go all the way to CO2, so CO is formed. So as we'll be talking about later, CO is formed when there's an incorrect mixture of fuel and air, and usually not enough air for the amount of fuel that's being combusted. You still get the CO2, you still get water vapor, and you can also get toxics. These toxic effluent products can be nitric oxides, or NOx, or SOx, sulfur dioxides. The nitric oxides can come from nitrogen that may be in the fuel or the air, and the sulfur dioxide can come from sulfur, which is usually in the fuel, but to a lesser extent lately with low sulfur fuels that are burning nowadays. Soot is another product of incomplete combustion, and you'd may be more familiar with that if you're using or testing oil burners. That would be the smoke spot test, would show up as soot. The smoke comes from raw carbon particles from the fuel that never even combust at all with air, never make it even partway to CO, let alone to CO2. Just raw carbon particles are being moved through the process and coming up as soot, so that's carbon. You still get the heat released, and here we also have excess air. There's some of the oxygen, more than enough oxygen is available to move through the system, and you'll get excess air as well as the air, the oxygen, and the nitrogen. So you get oxygen concentrations here, and CO concentrations, and smoke. These are some of the things that the combustion analyzer actually measures. It can measure the thermal energy by measuring the heat. That's the thermocouple and the probe of the combustion analyzer. An oil or smoke spot tester on oil systems can measure the soot. A CO sensor in the combustion analyzer measures the CO. An oxygen sensor measures the oxygen present. And there are some analyzers that alternately measure the CO2 present instead of the oxygen. And we'll show you about the relationship between those two in a minute. The nitric oxide gas here is one we'll be talking about in particular because that one can interfere with the correct measurement of CO. So why are we talking so much about air? I thought this was combustion. Well, air comes in different forms. It basically has different labels that we give it. There's ventilation air, that is the air that we control that comes into any kind of structure. There's the infiltration air, which is the air that's uncontrolled and comes in through unknown sources into a structure. There's the combustion air, which is the right amount of air that we need to make the combustion process happen correctly. And there's the dilution air when you're talking about an atmospherically vented system to make sure that you keep the dew point low in the chimney and you create the proper flow of velocity and effluent products going up the stack. So all four types of air here can come into competition, where if there is not enough infiltration air, perhaps after a building has been air tightened and air sealed, and we're relying upon that infiltration air to feed combustion and dilution. If that infiltration air is not available, it could deplete the way combustion is happening or the dilution air is happening. We did get a question here: when I'm testing an oil stack for soot, should it be sampled right on startup or should we wait 2 or 3 minutes after startup? Best recommendation I have is you wait until you're at steady state. So you'd be measuring the stack temperature, and that may be about 2 or 3 minutes after startup, but you want to measure the stack temperature and make sure everything is normalized. At startup, you will get a big burst of soot because the combustion system isn't stabilized. But think about for how long is the system running on startup and shutdown over the time it's running in steady state mode. It's the longer amount of time in steady state mode, and that's the right time to take the measurement to get an overall system number. So we have competition for air. Now let's move to what are combustion efficiency equations. The equations themselves are really a hybrid of thermal and combustion efficiency. The thermal part of it tells you the efficiency of heat transfer over your heat exchanger, because it's measuring the flue gas temperature, which is the temperature after it's passed over the heat exchanger and the heat should be extracted. And it also measures the combustion efficiency by measuring the oxygen and the CO. Primarily it's the oxygen, to see how completely combustion has happened and how much excess air is available. So those two numbers are put together by the combustion analyzer manufacturers to come up with a hybrid or a composite number that's called the combustion efficiency, the steady state efficiency. The high efficiency equations, if you were to get a perfect measurement of high efficiency, if you remember we showed on the slide a couple of slides back, water vapor at perfect combustion is always there. If there was a way to measure water vapor and measure the condensate, you could tell exactly what the high efficiency numbers were if you're using a condensing system. However, that's not a really practical way of measuring. So the manufacturers have come up with very good approximations for what they call the high efficiency operating, or that's for condensing furnaces or condensing boilers, to be able to use just the temperature and oxygen and tell you what the steady state operating efficiency is for the appliance. Now we'll get into some detail and we'll show you exactly what's happening in a combustion system for the concentration of the flue gas, and that's what's being measured. We gave some diagrams before about what kind of things are present, but now let's talk about how much. So on this axis going up is the flue gas component concentration, so we have less of it here and more of it here. We'll be laying down some lines here to show you as you move through different amounts of oxygen and fuel ratios, the air to fuel ratios, we'll see what happens to the various products of combustion as they move through here. So let's start layering on the information. So this first line we're going to lay down is called the stoichiometric line. That would be the line of pretty much perfect combustion. If you recall back to that simple slide where we just had three things, the fuel, the oxygen, and the source of ignition, and we just had the three byproducts of heat, CO2, and water vapor, that would be happening at the stoichiometric line, or line of perfect combustion. But since we don't have that, we'll be looking on both sides of that line to talk about incomplete combustion. So we have incomplete on the left side, and by incomplete in this case we mean not enough oxygen available for the full combustion. It can also be termed excess fuel side, more fuel than oxygen. And on the right hand side, complete combustion. Now on this side we will also see excess air, or excess amounts of oxygen, that will be showing up when the combustion analyzer is doing its test. So now we lay down the oxygen line. And an interesting point here is the oxygen line seems to emerge out of nowhere. There's no oxygen on the excess fuel side. Well, this is because all the oxygen available is being used up by the fuel in combustion, and there's nothing extra to go around. So this is an oxygen starved side, or incomplete, and now oxygen values start to appear. Again, we're looking at this probe is being placed in the flue gas. The oxygen values start to appear and start to rise as you're looking at more and more excess air coming into the system. This next line we'll lay down is the line for carbon dioxide, and we talked about that as showing peaking out, or having the most available at the stoichiometric line, or that perfect line of chemical balance. On this side, there's the air-to-fuel ratio isn't producing the maximum amount of carbon dioxide, and on the other side, the line drops off. This is kind of interesting. Why would this line drop off? What's happening over here to cause this drop-off? Well, it's actually, these are all volume concentrations of the flue gas. So as we add more air and more oxygen, there's less concentration of CO2. And that's what your combustion analyzer is measuring, concentrations. It's not measuring the exact, it's not counting every molecule, but it's how much oxygen in this sample. So how much CO2 in this sample. As we add more air, hence more oxygen, the amount of CO2 is diluted and it goes down. This line shows the carbon monoxide. And we do have the carbon monoxide line slipping over into the excess air area because this is more real world. You will get carbon monoxide even though you may have excess air. It's because the excess air is not present in every place and every single location where combustion is happening in the burner system, and air-to-fuel ratios and burning rates and flame stability may be changing to occasionally produce some CO and then again run at perfect combustion. So there usually is some CO produced even though you're beyond the area of perfect combustion. That's just the real world. Here's a line where we plotted, the red line is plotting the combustion efficiency. So this is to give you an idea of where the efficiency peaks out and where you'd see the manufacturer's combustion equation. So a peak, or the highest amount of efficiency available for the type of fuel and the equipment that you're running on. And I'll throw in a line now for smoke, and that would be the carbon particles. That's the purple line we just laid in down here. And again, it comes from very high levels when there's just not enough oxygen available and you're getting raw carbon moving through the system and forming carbon soot particles. But again, in the real world, that soot number or smoke number can come down and down and down when you get to have enough oxygen available to fully combust the fuel as you move through the stoichiometric area. And here's where most manufacturers in general would like to see you operating burners and boilers in a range where there's a moderate amount of excess oxygen, but not too much, such that you kill the efficiency, but also that you have almost no smoke present in an oil burner and very low levels on the black line of CO present. So this is the operating range on the excess air side. The thing to be careful, some of the older technologies, the wet chemical technologies, they call them shaker bottles or Fire-Rights, or the modified ORSAT method. You can notice that the CO2 line is not unique. For any concentration of CO2, there could be two values, one over here and one over here for the same concentration of CO2. So without some additional information, the CO2 reading by itself doesn't provide enough information as to what line you are, what side you are on versus excess fuel or excess air. Carbon monoxide can help with that. So a meter that has combined carbon monoxide and CO2 sensors is viable for determining a unique point in the combustion side to tell you which side you're operating on. So just to summarize, the efficiency equation gives you reasonable estimation of steady-state operating efficiency. And today's combustion analyzers estimate, all of them estimate the condensing mode, or give you the latent energy removal that's trapped in that water vapor. If you're in the condensing mode and testing a condensing furnace, it automatically includes that or calculates that. And you, again, we talked about not being able to tell that exactly unless you measure the volume of condensate, but these estimates that the manufacturers use are fine and acceptable for field use. So what isn't combustion efficiency or combustion numbers? Basically, it's a measure of stack loss, but it is not a measure of AFUE, or the annualized fuel utilization efficiency. It's not a measure of thermal efficiency, say from an ASHRAE standard, or the coefficient of performance, or a SEER, a seasonal energy efficiency ratio. It's none of the above. Combustion efficiency is basically a measure of steady state stack loss to tell you what the steady state operating efficiency is. So even though higher AFUE appliances will come from higher combustion equipment that's operating at higher combustion efficiency, they are not one and the same. Now let's take a look at what carbon monoxide is. We talked about carbon monoxide being one of the larger issues in terms of safety when it comes to combustion equipment. The CO comes, as we talked about just a few minutes ago, from incompletely burnt or oxidized carbon. So again, not enough oxygen for the amount of carbon present in the fuel. CO is very dangerous because it prevents oxygen absorption in the bloodstream, and it actually creates a new molecule in your blood. Usually you have oxyhemoglobin that's transporting hemoglobin or transporting oxygen around your system. It actually binds to the hemoglobin and creates carboxyhemoglobin, or COHB. That is very dangerous because it disables your ability of your hemoglobin to transport oxygen around your body. A quick analogy, if the hemoglobin is a pickup truck and it picks up oxygen in your lungs to transport to your cells and dumps it off in your cell, you pick up some CO2 in the blood gases and take them back to your lungs. That process hums along very nicely until you start ingesting CO. CO comes, it gets into that pickup truck, and it is epoxied to the bed of the pickup truck. It sticks there with a force greater to the hemoglobin, about 230 times greater than oxygen does, and it just doesn't want to let go. That pickup truck continues through your bloodstream to your cells on its merry way, but it's doing no good. It's delivering no oxygen. The deliveries have been shut down. So you start to suffer from oxygen deprivation in CO poisoning. CO comes from, we talked about not having enough oxygen available, and that can be when the fuel is running through too quickly to completely combust, or fuel-rich mixture. It can come from improper venting, when there's not enough oxygen being provided, not enough draft being provided to pull the right amount of combustion air through the system. It can be caused by flame impingement. We talked about having to have three things: the right amount of oxygen, fuel, and source of ignition or heat present to make that oxidation happen. If flame is impinging, it's taking away some of that heat energy to make that oxidation happen, and that will cause a cooled flame, which can cause carbon monoxide formation. Burner alignment also, as you can see illustrated in this picture here, burner alignment can cause some flame impingement. It can also cause the airflows and the combustion airflow to be incorrect and to be causing some carbon monoxide production. So what are the chemical characteristics or physical characteristics of carbon monoxide? It's something to be aware of. It's odorless. You can't smell it. Colorless. You can't see it. Tasteless. It doesn't taste like some gases do. It mixes well in the air. It's about the same density as air molecules, so it doesn't stratify. It doesn't pool near the ceiling or near the floor. It does follow, therefore, the airflow in a structure, so it'll get around in distribution air and ventilation air, whatever is happening inside the structure. The carbon monoxide is just going to go on its merry way along with the air. So that's a deadly combination on top of the fact that it's poisonous to people and animals. Those physical characteristics make it very hard to detect without using some kind of sensor. Carbon monoxide symptoms are persistent headaches, affecting your brain function, blurred vision, dizziness, nausea, then your muscular function, fatigue or drowsiness, and then getting into your lung function, shortness of breath, and then more brain issues, confusion. And you can also sometimes tell if there's a CO issue by feeling ill or tired when you're in one location, but then moving to a new location and feeling quite a bit better. It can sometimes give you the hint that you may need to be checking for carbon monoxide. So all these factors here, these bodily factors, the headaches, dizziness, fatigue, etc., those are all effects of oxygen deprivation. When we measure CO, we measure using a unit of measure called a part per million, or a ppm. 1 part per million, as its definition, is 1 in 1 million parts. So it's a very small quantity. That's what's being measured as a concentration in the gas that's moving through the combustion analyzer. In maybe a more physical sense, you can think about a 5,000-gallon hot tub or a larger hot tub or small pool in 1 dropper of oil. And that 5,000-gallon tank is going to be about 1 part per million on a volume basis. Another way to think about it, kind of drive home the point, would be to look at what is 1% in terms of parts per million. 1% is 10,000 parts per million. 1/10 of a percent is 1,000, etc., down the scale. So you can see it's a very, very small quantity. And next we'll be talking about the amount of concentration that has impact on as a poison. So here we're taking a look at various levels and the impact on people. And this is a combination of carbon monoxide safety and health standards as well as health effects, the actual impact on healthy individuals. So we have 9 parts per million is the US EPA and 13 is the Health Canada outdoor limit for carbon monoxide exposure. That's where the government would like to see you exposed to no more than 9 or 13 over an 8-hour period. The interesting thing here is we're now talking about not just the concentration, but the time, because CO is a cumulative poison. It builds up in your system. And by that we mean that the carbon monoxide has a half-life. That epoxying effect we talked about with the CO laying in the pickup truck in the bed of your hemoglobin, well, it does eventually come loose. If you keep it bathed in enough oxygen for about 4 to 5 hours, it will come loose, and about half of that CO will break loose out of those truck beds and then become available for breathing again. So the physiological effect is that it's about a 4.5 to 5 hour half-life of the concentration in your blood. That's why we talk about both time and exposure levels, because it is cumulative in the body, the physiological effect. So as you see, we're moving up here in the level where the U.S. Occupational Safety and Health Administration doesn't want to see a worker exposed over the course of 8 hours to more than 50 parts per million because of the negative health impacts. Now we start to get into the real serious issues with 200 parts per million exposure can give you a slight headache within a couple of hours. 400 parts per million halves that time in terms of which you get a headache. And then the sickness and actually really serious factors happen when you get into the 800 to 2,000 to 3,000 range of parts per million exposure. So it's very serious in very small quantities when you come to think of it. There is we threw in here the standard for ANSI, the NCC 21.1 standard, which is for the air-free flue gas measurement for combustion appliances, is required to be less than 400 parts per million when measured on an air-free basis. We'll get into that a little bit in some of the upcoming slides when we talk about appliance testing. But this is just to give you an overview from the levels that the governments want to see you exposed to versus the health effects. Now this is a review of what the BPI standards say, and I hope I'm up to date with them. I'll make sure I do a double check on these. But we're talking about 1 to 9 parts per million carbon monoxide would be considered a normal range or no action required. Then moving between 10 and 35, where advice would be given to ventilate. And between 36 and 99 parts per million, you're getting into an excessive area, and we should really stop and check actually ventilate and get people out of the structure and start to really get concerned. And then 100 to 200 is a medical situation, and it really should be, everything should be shut down and people moved out of the structure if you measure that much. We do have some of our personal CO monitors that we sell at TruTech. We have them set to go off the first alarm at 35 parts per million and the second alarm at 100 for these very reasons here, because these are very reasonable and appropriate action levels. This isn't a full course here in spillage and draft testing, but I did want to give you an idea of how the CO test results do play into a combination of spillage and draft, because we did talk about CO production and also ventilation and draft, talking about the required amount of air, in addition to messing with and causing CO to be produced due to not sufficient combustion air or dilution air. It can also affect the way the draft system operates or the vent system operates. So here's where really these two factors come together, both insufficient amounts of air causing CO as well as impacting CO getting out through the vent system. So this is just to give you an idea how BPI looks at it, but the main point of the chart really is to look at the fact that there's so many tie-ins between the amount of air and carbon monoxide being produced as well as being contained or distributed within the structure. So it just kind of drives home the point that we're really talking a lot here about air. Sources of carbon monoxide, don't always assume it's the furnace and hot water heater. There may be other things, other fuel burning appliances such as natural gas or propane ovens or ranges, even electric ranges, electric ovens especially, if they have buildup of organic materials. Those are hydrocarbon materials that, somebody's nice blueberry pie spilled over and burnt and crusted to the bottom of the oven. That can actually burn like carbon. It turns to carbon and can burn like an underfed oxygen situation, where it can also produce CO that has been measured during burners, etc. I was asked a question here, what references would I suggest for testing and fixing gas ovens and stoves that are high in CO? Rick Karg, K-A-R-G, has done a lot of work in that area, and I think if you simply Google the name Rick, R-I-C-K, Karg, K-A-R-G, he's from Maine. He's been doing work in this area for as long as I can remember in terms of ovens and ranges. You might find some interesting, valuable information from him. So we also have auto emissions, internal combustion engines, or even small combustion engines from yard tools, fireplaces, tobacco smoke, etc. A lot of different ways CO can be produced. So if you're measuring CO, don't always assume it's the major appliances. It may be other factors. When we're doing a CO test on a fuel burning appliance, the point of this graphic here is to illustrate that we do want to sample from entry to exit. That means from coming into the structure until we leave. We do want to sample around all unvented appliances because their effluent or flue gas products are coming right into the room, being contained in the structure and not leaving through a vent system. And then you want to check around the stack of vented appliances because that's where the reversals or problems with insufficient dilution air can cause your vent not to operate properly and to cause CO production. and anywhere else you might suspect CO taking place. Got another question here. The BPI table only references CO within the flue. Do the recommendations still hold if the draft is strong and venting safely? I'm going to have to table that question for a second here. Let me just move back a couple slides. It's basically, Mark, what I'm seeing here, if I'm reading the table correctly, if CO is between 100 and 400, and under natural event conditions, in other words, not worst case testing, either or condition can cause it to fail, or can cause it to fail the. Okay, right. I think he's got the answer there. All right, moving on. And we were talking about earlier about situations changing and why test an appliance that's not adjustable. Well, here's a good illustration because everybody does such a great job during routine maintenance. This is a true picture taken of combustion air intake in a boiler room. It was really hard to believe that any air can make it into that combustion air intake, and that's the way the system was designed, was to move air through that open grid, and that grid was so clogged down there wasn't enough air moving through, and that can cause a severe combustion to be compromised. Here's another issue. We assume everything's running okay, and this was a vent system that was damaged due to condensation. The water condensed inside the vent, causing, and then mixed with the flue gas, with the nitric acid and sulfur dioxide and the flue gas, then causing it to actually etch and eat through this metal vent material. So the vent wasn't actually no longer functioning as a vent because it had been eaten through by this by a combination of condensation in the vent line, which is probably due to not enough draft or some other, or maybe an improper installation with this type of material. So let's cover now combustion safety testing and using a carbon monoxide, or using the carbon monoxide function of your combustion analyzer. With all analyzers, it's very important to get the zero adjustment set. You want to make sure that the analyzer, you follow the manufacturer's recommendation to start the analyzer, usually with the probe in an area that you believe to be free of any carbon monoxide. If you do have it in a contaminated environment, it'd be great if you had a personal CO monitor and you could understand actually how much is present when you're starting up and zeroing it, and you could subtract that from the reading to see what the total concentration was. Or being able to actually move outdoors and start up the analyzer when you are outdoors. If you take a look at the video on our YouTube channel, and I'll be giving the address for that in a couple minutes, that will show you an actual live test that's being done with where we started up the analyzer outdoors to get the zero adjustment done. When you're measuring for carbon monoxide or taking a sample doing a combustion analysis in the flue, you want to be measuring an undiluted sample, and that means you want to be measuring a sample just after the heat exchangers, before the dilution air, if there's any dilution air present in your system. We'll cover how to handle high efficiency flues in just a minute. They have to be handled a little bit differently. These are mainly for atmospherically vented systems. You want to be measuring the core sample, which is a repeated area. It's called also the hot spot. It's where most of the flue gases are moving up through the stack. You use the thermocouple probe, the temperature probe, to find that core area. That gives you a more repeatable measurement. And then you want to be taking CO air-free or undiluted samples depending upon how the measurements are being taken and how they're being used. And this would, the CO air-free is perhaps a better measurement because it's less dependent upon the amount of excess air because it is subtracted out. We'll talk about how that's calculated in a minute. And then also measuring your combustion sources and unvented appliances, as we spoke about before. Got another question that came in. If you have a personal monitor and it reads 0, could you assume ambient's okay and turn on the analyzer indoors? Yes, I would say that's a safe assumption. Okay, we did promise to talk about CO air-free measurements. So an air-free measurement is basically a calculation between the CO sensor reading and the oxygen sensor reading. It's undiluted in that it removes all that excess air due to oxygen by making an assumption about how much oxygen and excess air is present to reduce the CO concentration. So an undiluted CO reading will always be higher than the raw CO reading. It allows it to correct for excess air dilution. So it's just simply a ratio that's done inside the meter. So it's either CO undiluted or CO air-free on your combustion analyzer screen, and it's correcting for the excess air dilution and giving the raw CO that's present. If you could just remove all that excess air and move it back to the stoichiometric line, here's how much CO you have. In order to make that measurement, it requires an oxygen sensor, which means you have to be using a combustion analyzer. There's still some CO-only meters out there, although those are less and less prevalent as the prices on combustion analyzers are coming down. We're seeing more and more people using combustion analyzers, which is a good thing. And this air-free measurement is usually used for appliance measurement for unvented ovens and ranges, because there the oxygen level is so high when it's unvented and you're taking a sample that you really need that in order to be able to interpret an undiluted reading. But it's also gaining some popularity and being used for in-stack measurement because it does get rid of that variability that comes from the changing oxygen levels. And it does relate to an ANSI standard, American National Standards Institute Z21.1 standard, where we talked about already less than 400 parts per million measured on an air-free basis in the flue gases for most appliances. So let's talk a little bit about NOx. We promised to come back to this point. NOx, again, we mentioned, comes from the nitrogen either in the air or sometimes in the fuel, and it produces a variety of species of gases, nitrogen dioxide, nitrogen dioxide, nitrogen monoxide or nitric oxide, dinitrogen pentoxide, and other species. All those species of NOx can be produced, but they're called as a family, NOx. Again, we mentioned created by nitrogen that comes through in the air, in the flame, or it's produced in the flame, or comes through in the fuel. And then the nitric oxide tends to be the highest concentration, the NO gas. It does convert to NO2 when it goes into the air, and it takes about 30 to 40 minutes for it to dissipate and to change over into NO2. However, when it's in the form of NO, and you're measuring especially in a flue, and it is the highest concentration of all these species is NO, usually about 80 to 95% is NO. It can fool a CO sensor. It's also considered an acid gas, which on an unprepared, unprepped CO sensor can fool it into thinking there's CO present. For example, about 100 parts per million of nitric oxide gives you about a 40 to 50 parts per million reading of false CO. And I've seen numbers anywhere from 60 to 160 and higher NOx from residential combustion systems. So it is present, it is a factor. So that is going to add to your CO reading unless it's filtered out. And now all the manufacturers are providing filtered NOx filters on their CO sensors to give you the pure reading. One other point, hydrogen does cause a cross interference on a CO sensor, but that's usually not an issue unless you're at ultra low excess air values, and that means very high efficiency burners, that kind of thing. That's only where you're going to see this hydrogen issue. So there are special sensors that deal with the hydrogen concentration, but they're usually not of note or of value in the burner boiler and residential testing market. And so our advice, if you want an accurate CO reading, never measure without a NOx filter. It comes standard on Testo products. It's included or available for all the Bacharach products and the other manufacturers out there. And it may be an internal sensor or an external cartridge built into the sensor. This illustration here shows the internal NOx filter cartridge on a Testo 327, but sometimes these filters are built into the sensor and not removable and not replaceable. but it's best to ask or check with the vendor you're buying them from, or check with the manufacturer's literature to find out if you do have a NOx sensor. But it's strongly recommended you make sure it's present to make good in-stack CL readings. Here's an example, and it's using some older equipment, so this, but this does draw home the point. This was an analyzer that did not have a NOx filter built into it, or an external NOx filter applied. Showed 27 parts per million CO. And here's an analyzer that CO sensor was filtered for NOx and was also happened to be measuring NOx. So you can see at about 40 parts per million NOx, it came up with a factor where it impacted the CO reading on this unfiltered CO meter and gave it an extra 21 parts per million. So actually 6 was present, but this one showed 27. And that extra 21 came from those 40 ppm of NOx, where we talked about a 40 to 50%. In this case, almost exactly 50% of the NOx was read through by this CO sensor as CO. We did talk about personal monitors for CO and even oxygen for confined space entry, and this can be true in commercial situations when you have oxygen deprivation. But they're very good to have on hand. They'll help you save your life or the life of someone you're working with, or the property you're working on. Many of them you can keep them always on. Some of them, like the Sensit P100, have a very long battery life, basically 2 years you can keep it on. They give auditory and visual flashes or beeps, and the Sensit does happen to vibrate to give you that physical interaction that you do have an alarm situation happening. And they can, as we mentioned before, can be used, the reading on the display can be used to help you understand if your area is safe to power up your meter in to get your background or zero out your CO sensor. So ambient CO testing now. We want to zero the analyzer outside. It's important to test at all levels of the home, even though the CO is not going to pool at the higher or lower levels. It does move through with the ventilation air moving through the structure. So you do want to test at all levels. You're never sure where you're going to find it due to vent leakage or propagation due to the air handling system. Testing around the heating appliances and hot water tanks. You want to do that as well as make sure that if your levels exceed 35 at any time, this again goes back to the BPI recommendations, turn the appliance off and make recommendations or repair recommendations, and if above 100, vacate, call in an emergency, and leave the front door open on the way out to make sure the ventilation air gets in. Unfortunately, this leaving the front door open compromises kind of the trail of where the CO is coming from, but in this case it's better safe than sorry. So in the case of, again, just a little further information about ambient testing, we want to look at testing the with pressure conditions that change, and we talked about a dynamic environment with the fans and the pressure, fans, ventilation fans, house fans, kitchen fans, bathroom fans that could affect the combustion air that's available. Doing the room air and the flue gas monitoring together, room air to see if anything's leaking into the room, and the flue gas to see how much is being produced. And it's very convenient to have this printed up, the information printed up with the date, the time, the type of meter you're using, the serial number, etc. It gives you a very good track record, or very good record to have of your examination. Sometimes a question we get to is instrument accuracy versus resolution. Resolution is the counts, what can be displayed on the screen, and most of your digital analyzers will be about 1 part per million resolution. However, the accuracy may be in the area of about 5%, plus or minus 5%. That's usually 5% of reading, which means if you're reading 100 parts per million, it could be plus or minus 5 parts per million. So it could be actually anywhere from 95 to 105 parts per million. Going back to draft testing, or testing for draft, because we talked about the importance of proper amounts of dilution air. The draft helps remove flue gases, and this is the case of an atmospherically vented system. Things are different, though, when we talk about condensing or high efficiency systems. It does help control the air flow through the heat exchanger. You can see at the merge point here where the air is coming around the heat exchanger and moving up the dilution air. This actually a blockage or a change in the amount of air moving through the system can affect the airflow over the heat exchanger. We're also looking for the draft to be established within 5 minutes of startup on atmospheric compliance because that's due to the buoyancy effect of the heat going up the system to create the pull that in a natural draft situation. And we want to measure when it's at its maximum. That would be when you have a situation of a hot stack or a warm stack, and that buoyancy would have been established. Here's a quick illustration of a draft hood. It's something you may or may not encounter in your testing, but here in this case it serves to kind of draw the line between different areas where you're making samples and doing tests. It's a good illustration for that. So the undiluted flue gases would be coming up through the bottom portion of a draft diverter or the draft hood. You'd make the combustion test in this area here. This is where we're talking about the undiluted flue gases, which are under a positive pressure moving through the system. The dilution air can move through with a positive or a negative pressure. It can either be pushed through or pulled through. And the diluted flue gases here, you would be measuring a negative pressure because you'd be measuring the pull, the draw that they have to move flue gases up. In this case, the draft test is done at about 2 diameters past the hood, and we have some good references and resources on that. If you want to see some more elaboration, just drop me a line, or we can do so after the session's over. I wanted to mention that spillage occurs when the draft is not strong enough or it's overcome by a negative pressure in the room that pulls against the draft, or it's not strong enough to pull the undiluted products of combustion up the stack. And here's a couple of impactful pictures here to talk about why there might be too little draft when there's a competition for the air. We talked about that very early on. Not enough air available. Blockage in the chimney, which stops the correct flow rate. A poor system design from the beginning, or perhaps even duct leakage, which causes a negative pressure zone to be established near the heating appliance. Too much draft can be caused by an oversized chimney. It's just moving way too quickly at too high a velocity. Excessive stack temperatures, there's too much buoyancy. Again, it's not designed correctly for the situation. Or if there's a power vent that may be causing too much flow through the system, higher than desired flow. On this page, we promised to talk a little bit about heat exchanger examination. Well, there are really three different steps or 3 different modes of doing it. One is simply the flame disruption test, where you look to see if the blower cycling on and off disrupts the flame. That means there's communication between the combustion compartment and the distribution air side when there should not be any. If that happens, then there's likely a problem with the heat exchanger that's blowing the distribution air into the combustion compartment, and that's a bad thing. There's a breach in there that shouldn't be. You can also look for minute airflows at the heat exchanger cell exit with the combustion turned off, but with the blower cycling on. Sometimes we've used a hot wire anemometer to actually look for small airflows at the heat exchanger cell exit, and this would be on an atmospherically vented system. There's also visual examinations that can be done with various mirrors and visual inspection scopes to actually get inside and take a look at the integrity of the heat exchanger itself. And then there's the chemical test. The chemical test involves filling it's also called a HET kit. It used to be manufactured actually by Sensit, but I'm not sure they manufacture anymore. But there would be a methane-filled heat exchanger chamber blocking off the vent with some form of balloon or blockage, and then using a gas leak detector on the distribution air side to see if any of that methane is making it over. Tends to be a little bit more of a cumbersome test, and probably one of the reasons why it fell out of popularity. One of the sodium salt or sodium ion salt spray tests, where you look for a discoloration with a salt spray. But one of the more popular ones is the oxygen change, or the O2 test. And I think we have a slide on that next where we go over that in a little bit more detail. And then finally, the manufacturer standard, basically, to our best of our knowledge, is about a 1/8 inch hole is allowable for equivalent leakage in a heat exchanger. They don't feel they can get any tighter than that. And this is an impossible test to perform in the field. So some of these intermediate tests were developed, and some of them were published in a GAMA, which is the old Gas Appliance Manufacturers Association, and a RSES, or a Refrigeration Service Engineers publication in 1986, if you wanted to reference that. So in the visual exam for the heat exchanger, you look for rusting, staining, cracks, as illustrated in this photograph, failures at the weld, holes, pitting. And one comment here is many times the heat exchanger issues are not related to poor heat exchanger design, but more related to either maintenance or installation. If there's insufficient flow over heat exchanger, the flame's not going to be in the right place, burning with the right intensity, perhaps overheating the metals in the heat exchanger, or if there's excessive fuel pressure, which causes too long of a flame, again, the flame being in the wrong place at the wrong time. So these are why the manufacturers have specific setup parameters for airflow and for fuel pressure to make sure that the components don't get degraded by poor installation or poor maintenance. Here's a little detail on doing the chemical O2 test, where we start the furnace with the blower off, and then watch for the oxygen and the CO levels in the flue with your combustion analyzer to stabilize. And then as the blower starts to cycle on, to very carefully watch the oxygen and CO levels as it starts up. And if the oxygen increases or decreases, or the CO increases, there's a high probability that the blower compartment is talking to the combustion side, which means there's a breach in the heat exchanger. And it'd be a good idea to repeat this test to verify and make sure you've seen those levels. And we're talking about levels in oxygen of about 0.5%, and CO in the range of 50 to 100 parts per million change. So you do have to really take a close look at those readings and make sure that those are changing at those high levels. And this would warrant further examination and perhaps visually to try to find the crack or the leak in the heat exchanger. We do sell a book at TruTech called the Furnace Examination Guide. It's also called the Heat Exchanger book. It has in it all major makes and models from North America of the common failure points for cracks or leaks in heat exchangers. And like a lot of things tend to, when they do fail, they fail in the same area, and this book compiles them all. So that's a good thing. If you're going to be doing heat exchanger inspections, you can do this chemical test. If it gets you on a trail of suspicion, then you crack open your book and take a look at what the common area of failure might be. Then you go look at it. It can save you tons of hours of inspecting a whole heat exchanger when you know where the common failure points are, and that's what this book does. So in our summary here on heat exchangers, facts on cracks, cracks or holes do not necessarily cause CO, but because they interfere with the airflow or can interfere with draft, they could actually cause CO. They may not necessarily cause it, but they could cause it. Cracks are definitely pathways for flue gas to mix with the room air, or vice versa, room air to mix with the flue gases. You might not think that's as important, but if the, say you have a induced draft furnace and it's looking to pull so much air, it's such and such a pressure with its pressure switch, if it's pulling air from the distribution air or the room air side and it's not coming through the combustion system, it may be interfering with the amount of the amount of combustion air coming through because it's pulling air from the distribution air side. It's kind of a little advanced topic here, but leaks both ways can influence the system. It's not just a one-way leak that can be dangerous. Corrosion or discoloration and mineral deposits can be signs of cracks. They may look like rust lines. And some of the underlying reasons why cracks or corrosion may occur because of uneven airflow or insufficient airflow over the heat exchanger. Clogged filters can cause not enough airflow to be present. Excessive cycling, heating, and cooling, maybe because of high fuel pressures and improper airflow or excessive airflow over the heat exchanger, and improper venting that may cause temperatures to back up inside the heat exchanger. So again, setting up and maintaining per manufacturer's specifications can save you from these issues with heat exchanger problems. Other equipment that may require testing includes hot water heaters, vent-free or unvented space heaters, gas ovens, and cooktops. And again, we had the question earlier about, and I've given the resource of Rick Karg, K-A-R-G, as being a good resource for oven and cooktop type testing. The purpose of this slide, and this, by the way, this was created using a Testo 330 combustion analyzer and software called Easy Heat. Very powerful because it gives you this kind of strip chart recorder output on a real-time basis. And I've used it that way. It's a very, very handy tool to see all the dynamics going on. But the basics of this slide were basically to show that there are a lot of dynamic things going on. When oxygen levels change, efficiency levels change, carbon monoxide levels change, stack temperatures change, all kinds of changes happen at all kinds of times. Combustion air, this was a ventilation issue, but in this case, the point we want to drive home here is you need to have a digital analyzer with a multi-line display telling you this information, important information, because it's changing all the time and everything is interrelated. We wanted to talk about some of the interrelationships, how to interpret some of the results, and this comes, we do have a higher level course which is under development to give actually more technician level diagnostic and troubleshooting advice. But things like a low or falling O2 might be due to heat exchanger cell blockage or blocked vent or collapsed liner, or perhaps even recirculation in the combustion air zone, or lack of combustion, dilution, or ventilation air. So these are some of the factors that can cause your combustion analyzer to show a low or falling O2 reading. And a quick illustration here now. Oh, by the way, going back here, these kind of examples and this kind of information, we do have a free combustion application guide that Jim Bergman developed. It's available for download on our website. You can just search for the combustion guide, or it's product number 1449. It's pretty easily found, but it can give you a lot of this in a text format if you're interested in that. When you go to test an atmospheric or warm air furnace, you want to make sure you're in the steady state operating mode. Again, warmed up, the vents warmed up, the heat exchangers warmed up, and you're running at that steady state. You do want to sample around the combustion air zone for carbon monoxide, and then do your testing in the heat exchanger cells for efficiency and for CO. And checking CO around the burner area, make sure there's no problems with that. Then conducting your draft test in the stack after dilution in the area up here, and also making sure your fuel pressure is set correctly. So these would be some of the things that a technician would follow, and again, we cover these in a little bit more detail in our under development combustion course. Testing a condensing furnace is a little bit different. You again wait for steady state operating conditions, sample around the burner. Sample efficiency in this case would be in the plastic vent pipe, and that would be if the manufacturer or the authority having jurisdiction allows you to do so. And if not, you may have to sample. If not available to sample here, you may have to sample in the termination, which we'll show you a picture of in just a second. Here's a picture of a high efficiency system, a condensing furnace, where you'd have to do the CO test in this type of vent. And at this point, the efficiency numbers would be pretty meaningless. you can't use them because they're too far away from the heat exchanger. Remember we talked about the thermal efficiency being a factor there, measuring near the heat exchanger. Here you've had too much temperature drop, but you could measure that oxygen level and get an idea about efficiency, and definitely the CO level, how much CO is present, could be measured at this point. In some situations you may need to test on B-type vent or type B vent, and this is okay when it's necessary and it's not in violation of the local code or the authority having jurisdiction. The basic parameters to follow are that the inner sleeve hole only be as big as necessary to fit the probe of your combustion analyzer, and that after testing you do actually seal the inner sleeve hole with a high temperature non-hardening sealant, and this is a must that you seal the inner, and also seal the outer hole with a high temperature with the same sealant and a patch of aluminum tape. And this information comes from 4 major manufacturers: Metalfab, Simpson, Selkirk, and Hart & Cooley, in letters that were issued to that Bob Dwyer and Rudy Leatherman helped collect in the mid-90s here, early 2000s. And if you want to get those letters, they're available on our blog, and I've got a short link here if you want to write this down. It's www.bit.ly/B-VENT. So B-vent, but an uppercase B and an uppercase V at bit.ly, at the bit.ly website, which is a short link. It'll take you right to our blog, and you can download a PDF of those letters. When we get into testing larger equipment, the parameters change a little bit. The probe insertion place now is about 1/3 to 1/2 of the way into the stack. You're not so much looking for that core sample in this situation, but you do want to hit a consistent, repeatable point. You're going to have to sample several firing rates, because that's the nature of the beast when you have these larger equipment. In many cases you'll operate the analyzer, shut the analyzer or turn the analyzer off, make some adjustments, and go back and continue an iterative process. In this case you're tuning for maximum efficiency, safe combustion, and clean and efficient combustion. And as we say all the time, you do definitely want to follow the manufacturer specifications to optimize the equipment and to have it installed correctly. So when we get to atmospheric gas-fired burners, some of the typical readings you might see would be 4 to 9% oxygen. If you remember back to that chart that we drew, showing the oxygen on the excess air side, and this is where you'd be measuring 4 to 9% oxygen. The carbon dioxide measurement would be between 6.5% and 8%, and that would be usually calculated from your analyzer. Stack temperatures 325 to 500. Draft in the 0.02 or 2/100ths of an inch water column to 4/100ths of an inch water column. Negative draft. Remember we talked about draft being negative at that point after the dilution. Carbon monoxide usually about less than 50 ppm when measured on an undiluted basis. And again, refer back to the manufacturer's specs to provide the most keen information for the equipment you're testing. On a draft-induced or power burner, the oxygen numbers do vary a bit, and here they're moving between 3 to 6 and even as high as 13% in some situations, higher levels of oxygen, with lower levels of carbon dioxide between 8.5 and 11%. Lower stack temperature readings 275 to 500, and the draft between 2/200ths and 4/100ths of an inch water column, and the carbon monoxide less than 100 parts undiluted. And these are typical readings. Again, you need to refer to the manufacturer specs to get the exact numbers for the equipment you're working with. And in oil, the oil-fired power burners, 4 to 7% oxygen, carbon dioxide 10 to 12.5, and stack temperature 325 to 600, and the draft over fire 2/100ths and 4/100ths negative before the barometric damper, and less than 50 parts of CO undiluted. We talked about the formation of carbon particles or soot as a sign of incomplete combustion, that you're on the wrong side of the curve or on the wrong side of operation. Usually 0 spot is recommended Greater than 1 smoke spot is usually not recommended because it's in addition to showing that you're incompletely burning, not getting the value out of your fuel, it can also increase fuel consumption by actually forming an insulative layer inside the refractory of the burner compartment. We did want to make sure you're aware that Testo does have a digital smoke spot meter, which takes the last page here. We're talking about the manual smoke spot. Testo and Bacharach both make one. Bacharach was one of the originators of this, and the scale for it, the Shell Bacharach scale, where you actually pull a gas sample with something similar to a bicycle pump, but you pull it through a filter material and then read it up on a scale to see what level of soot you have, the smoke spot. But Testo has developed one that actually measures without pumping, uses an optical sensor to determine the smoke number. It can transmit or beam the data to a Testo 330, and it also has the ability to measure in tenths of an inch, or excuse me, tenths of the smoke spot number, so higher resolution on the display here. And just a couple quick points here, and I apologize for running over, but I knew I would. Combustion analyzers, you do want to take care of them. There's some things you need to do to take care of your investment to make sure that your results, which is your reputation, your name, are preserved. Annual calibrations are recommended. TruTech now does calibration and service on Bacharach and Testo combustion analyzers, both brands. We do have a site on our web page for that. Want to make sure you're aware of that. www.bit.ly/TTT uppercase -cal uppercase CAL bit.ly/TTT-cal will get you to our calibration page, or you can just search for it normally, but this is just a short link here. I want to make sure you're aware of that because it is so important to get the proper calibration and service done on your analyzers, especially before you go to use them for the first time in the season. And it's getting to be chilly out there. I've seen some leaves fall here in the Northeast. So there are some other service factors or points of service, things like the pump that pumps the flue gas through, the water traps, filters, and probes. You want to make sure those are all in proper working condition, and those things are examined during the calibration service that you'd get from basically from anyone that does service and analyzers. You do want to pay attention to storage temperature limits, especially because condensation inside the analyzer, if you go too low a temperature, can actually freeze and crack things. So you want to make sure you take good care of the equipment and you bring it in during the coldest weather. You also want to pay attention to a fresh air purge. If your analyzer shuts down during the middle of the test, it may be the type that has an automatic shutdown sequence in it when it sees excessive levels of CO. And at that point, you're going to have to make sure that you don't overrange the sensor. And I know the Testos, some of the Testos have overrange protection, but if they do shut down, you immediately want to start them back up breathing fresh air, or if you see your Bacharach go over range, you want to make sure that you get it out, the probe out of the stack breathing fresh air, because you can cause a CO sensor to get drunk and actually cause it, kill it if you give it too much CO exposure. So you do want to pay attention to sensor overranging. And then just a note about proper printer paper. Some people try to shortcut and use a printer paper that fits in the cartridge, but many times the traction and the density isn't correct, and you end up with hassle. So it's worth it to get the correct printer paper from the manufacturer. So here's a quick overview of the new toys. The Testo 310, which is their new class product. Actually, these are the list prices shown here. We're selling some of these. Just to interrupt for a second, we do have a question. What ppm readings a CO would overrange a CO sensor? It's best to check the manufacturer spec and see what their measurement ranges are. Generally speaking, above 4,000 would be considered getting into the overrange. Some meters, though, can take up to 10,000. So the best thing to do is to check your instruction manual or your sales brochure on the product or the website you bought it from. See what the maximum range is and make sure you never exceed the maximum measuring range. Going back here, the Testo 310, it's a sub $700 equipment. There's the oxygen CO sensor, draft sensor present. The 320 has a color graphic display, contains many useful probes. It's basically a replacement for the Testo 327. And then you have the new FireRate Intech. Actually, I believe today we're filming a new video on the use of the Intech or the Insight Plus. I'm not sure which one's going to be filmed today, but we do have a video up on the Testo 310 on our YouTube channel, and pretty soon you're going to be seeing videos on the back rack. I believe the first one we're doing is the Insight Plus for the back rack. So these are, color graphic displays, memory storage, a lot of new features, not a lot of new technology, and the prices are really getting in the interesting range here for everybody to consider equipment. So here's an illustration of where we do a lot of our video training. Jim Bergman is the key producer of most of this video training, where you're going to find this webinar recorded. You're also going to find other live videos that Jim has shot. YouTube.com/JimBergman3, JimBergmann, and the number 3. And you get to our page and see our catalog. There's 40 videos there now. We're probably going to be adding them at the rate of a couple every month. And these are going to be new, right from Jim's heart and Jim's brain, giving you some ideas about how to better use the equipment and how to get more functionality out of it. So as we wrap up here, your BPI number should have been entered at registration time in the webinar registration. If not, just drop an email to Marilyn@TruTechTools.com with your name, the date of the webinar, and your BPI CEU number, or the BPI certificate number. And we submit the reports within a couple days, and then BPI takes a few days to log these in before they're reflected in your BPI account. We also offer a $10 gift certificate to TruTech for completing a product review of this webinar. So we would encourage you to do it. Just go back to the webinar page, which is TruTechTools.com/webinars, and find the webinar icon, and just click the write a review box beside it. When we see the reviews pop up, we do this I think about once a month, we'll go in and we'll gather up those people. And it's a positive or negative review, but basically it's to incentivize you to make the comments, not to put any words in your mouth. So I'd like to thank you for your time and attention attending the session today. I appreciate the questions that I've received here. You'll see the listing for the session on our webinar page, and there'll be a little highlight where it says for a recorded session, click here. For a copy of the slides, click here. That's where you're going to find these. Again, the recording will be posted in about a day. The slides are already up there right now. So you can see those links on our webinars page. You can also, as I mentioned earlier, download our combustion guide at TruTechTools.com/combustion guide. And if you want to see those videos again, our YouTube channel, or send us an email, either myself or Jim, we're co-owners here, Bill at TruTechTools.com, Jim too. And if you want to talk to our sales department, send an email to Eric or Josh at TruTechTools, and calibrations and service, William or Bill Sutherland. He goes by William at TruTechTools.com. So we appreciate your time and attention today. Feel free to give us a call at any point. And we're going to finish up here, and thank you for your attention today. Appreciate it. Take care.